All right, well, we'll get started. It looks like it's a couple minutes after 11:30, so just want to say good morning, everybody. Thank you for joining Rumsey in our continuing Locked In series being hosted by Rumsey Specialists. My name's Sean Huber. I'm one of the automation specialist group managers here at Rumsey Electric. Today, we'll be continuing to take the series on the power side of our business with a presentation around VFDs and line side protection. So with that, I'd like to introduce Rick Archer. Rick is one of Rumsey's drive specialists here at Rumsey, and he's been with us for about 14 years and primarily covers the New Jersey and Philadelphia region for us. However, he's also covered or helped to cover the area with two other drive specialists, uh, Mike Lohr and Jared Roberts, whenever Rick's not available. So from that perspective, they do work as a team. With that, Rick, if you're ready, I think we can hear you. I'll let you take over.
Thanks, Sean. Good morning, everybody. Like Sean mentioned, my name is Rick Archer. I'm one of the drive specialists, and we're going to talk about VFD line side protection, and that's going to include pretty much any hardware device that you would put in front of a VFD. A little bit about me. I'm one of the Allen Bradley drive specialists. I've been 13 plus years in my current role as a drive specialist. I have 30 plus years of industrial automation experience, which started as an industrial electrician for approximately 10 years, and then I got into control systems, programming, VFDs, you name it, whatever it took at Lennox, China. And then I spent 6 years before that in the U.S. Navy working on a missile system. And you can see by the pictures that I selected, my passion, obsession, or other things that I could call it, when I'm not working on VFDs or taking care of other adult responsibilities, is racing motorcycles. And the picture on the right is actually me on a day off down in West Virginia practicing for a race weekend. And I'm obviously on my phone emailing Sean about, and he asked me what drive should I use. And I look up at my number plate and it's 753, of course. So I responded back to him, use a PowerFlex 753. We've already had two other webinars during our Locked In series around VFDs and the power side of it. The first one was correcting harmonic distortion with active harmonic filters. That's available to watch on demand if you weren't on it. And then we also had installation considerations for modern VFDs. Again, if you weren't on it, you can watch on demand. Today is line side protection, and then on May 26th, we're doing protect your motor. And the way we put this together is the installation considerations for modern VFDs was a 30,000 foot overview of a drive system. The line side protection is going to cover the input, and the protect your motor is going to cover the output. I'll go down to about a 15,000 foot level with the line side protection. These are some of the user manuals, installation manuals, technical data manuals that are available for what I'm going to discuss. The one that's referenced a lot is our drives installation manual. The proper name for it is Wiring Grounding Guidelines for PWMAC drives. It's got a lot of reading. It's got a lot of best practices. It's actually a very good manual if you have some time and want to read it. So again, I'm going to cover everything that goes in front of a VFD, and you can see I highlighted it, what's going in front, and I'm going to cover basically four different things: the grounding schemes, the source impedance, overcurrent protection, and harmonics and harmonic mitigation. And I'm only going to go to a 15,000 foot level because any one of those topics could be easily a half hour, an hour, or with harmonics, a couple days to go down to the ground level. Okay, so the first area I'm going to talk about is the grounding. Again, that could be a topic in itself, but there's three basic types of grounding. You have a solid ground, a high resistance ground, and an ungrounded system. Some of the symptoms, if you don't set your drive up correctly or you're not familiar with what type of grounding system you have, can be severe equipment damage. You could have overvoltage faults and ground faults. Our Rockwell Allen Bradley drives are able to handle any of those three types of grounding schemes. Some of our competitors cannot, so that's important to point out. And in the Rockwell world, it used to be those three. Now it's pretty much solid ground or a less than solid ground, ungrounded. So we don't have a high resistance ground anymore. So a solid ground Y is the recommended. Again, there are some ungrounded or high resistance grounds in our area, but the reason that the solid ground is the recommended and the best is it gives you a control path for common noise current. It's consistent line to ground voltages. You can put in surge protection devices. Rockwell sees fewer technical support calls when drives are used in a solid grounded system. And a solid grounded system is the only way to accomplish and meet CE compliance and UL compliance. This is the high resistance ground Y grounding scheme. Again, if you're not familiar with your plant, you put a drive in set up for a solid ground, you will see some erratic behavior. And here's the ungrounded system. Again, if your system uses an ungrounded power distribution system, you'll probably be aware of it, and you'll just have to pay attention to when you buy a drive and install it in your system. And the reason that it's so important on a non-solid ground, if you do not disconnect the MOV input filter cap jumpers and the DC bus common mode caps, you could either possibly damage the front end of the drive or get very erratic behavior. With a solid grounded system, you want both of those jumpers put in place. Again, you can meet UL, CE, and you'll have less noise. That blue sticker on the bottom right, when you buy a drive, just a standalone drive, that sticker will be on the line connections, and you want to verify your grounding scheme before putting the drive, powering up the drive. And if you are a panel builder or machine builder, you want to take that tag and put it on wherever the customer connection is going to be for the power. Many times I've seen that sticker, people rip it off to put their line power on their drive, and they throw that sticker away without paying attention to it. Next topic I'm going to talk about is source impedance. And some of the symptoms if you have a drive installed without going through the upfront work is you may have frequent input failures, drive failures, the SCRs failing, over voltage or under voltage faults. One of the things to take into account is the maximum supply kVA, and a line reactor helps with line sags and spikes. And our user manuals and our technical data manuals, if you look in the example and highlighted, each of our drive ratings have a max supply kVA that you can supply the drive with. Along with source impedance, one of the most frequent questions I get is, when should I add a line reactor? And here's the bullet points for that. If you have low line impedance, if your supply transformer kVA rating is 10 times then a drive without a DC link choke, or 20 times for a drive with a DC link choke. If you have power factor correction capacitors on your line, frequent power interruptions, intermittent noise spikes, or if your incoming voltage imbalance is greater than 2%, which can cause large unequal currents in a drive. Now, when you look at that supply transformer kVA rating, the next question is, how do I know if my drive has a DC link choke? So do I use 10 or 20? If you look in the technical data manuals for our 520 or our 750 series, part of the electrical specifications, they tell you whether that drive has a DC link choke. And our 520 series, it's only for frame E drive ratings, the larger of our 520s. All of our PowerFlex 750 series have a DC link choke less than or equal to about 4%. And the reason that the small drives like the 520 don't do it, it's literally just a manufacturing cost. It's not common to put the DC link chokes across the board on small drives. Next question is, how do I know what impedance line reactor do I put in front of my drive? 3%, which is 3 and 5 are the common line reactor impedances. 3% are good for absorbing line spikes, and they avoid some nuisance tripping. 5% are typically put in front of a drive to try to meet IEEE 519. And just as a note, the 5% are not used typically as load reactors. And then if you have a lot of voltage spikes, you want to use a 3% reactor, and they're effective at that. And with that, I want to show, this is a waveform where they took a drive, they put the oscilloscope on it, and they actually hit it with a capacitor to simulate a transient. And you can see there, without a line reactor, this drive, the DC bus, was normally operating about 677 volts DC. When they hit it with the transient, the DC bus jumped up to 806 volts DC. The normal trip point for overvoltage is 820 volts DC on our drive. So see how close that got to an overvoltage fault. And then you can look at just the normal operating current peaks and the peak during the transient. This is the same waveform with the same condition and induced transient with a line reactor in front of it. You can see the DC bus has a little bit lower to begin with. The peak current is lower with the line reactor in front of it. And even during the transient, my bus voltage only jumped up to 653, and my peak current was way less. So again, the effect that it has on the electronics, the SCRs in the front of the drive, is much reduced with the line reactor. Moving on to the drive input as far as fusing, circuit breakers, and overcurrent protection. Our manuals all have the recommended fuse types, whether it's you're doing IEC or trying to meet UL. And then we also have that in the table, the circuit breakers and the proper circuit breakers for using in IEC or UL applications. Here's an example of that table that you would look in during design for the 520 series, and you can see it's got the drives broken down. This is just a snapshot. We have covered them all. It gives you the input amps, the maximum amps, any contactor that you want to use, IEC, the minimum and max fuse rating, the circuit breakers, and then for UL applications, the same thing, the type of fuse, and the 140M that you would use for that. Again, this is out of the 520 series technical data manual, and it will also be for our 750 series. You will look in the 750 installation manual. One quick caution on input contactors. Again, today I'm going over everything that you would put in front of a drive. So there's a note in the user manuals and the technical data manuals. If you put a contactor or other device that routinely disconnects, I'm not going to read the whole thing, but basically, if an input device is used, operation must not exceed 1 cycle per minute or drive damage can occur. And I made a note to here about if you have that input contactor in there for a safety reason, you might want to consider installing a VFD with integrated safety circuit to replace the input contactor if you need to have frequent power cycling. And that can be intentional or unintentional. I've actually had a customer that had an input contactor tied to their e-stop circuit, not knowing the operators were cycling it very often during times when the process was interrupted, and the VFD failed. So we went back in, put a safety circuit in the drive, and eliminated the input contactor. Next topic I'm going to touch on briefly is CE conformity. Our drives are rated CE, but CE is not just dependent upon the drive itself. It's a system requirement. And you can see just by this diagram, I may need an EMI filter. I have to have my grounding in a certain way. Again, I need to be in a solid grounded system. And then if you do need to meet CE, if you're building a machine or you're shipping something over to Europe where you need that CE conformity, all of our manuals have what is required from a system standpoint, how to meet CE, the different categories you may need. And if you look at the example and the additional installation requirements, you may need input output cores, you may need only output cores. So again, each of our drive catalog numbers, horsepower ratings have the requirements to meet the different categories of CE. Now here's where I'm going to stay at 15,000 feet. I am going to go over harmonics, and this topic could take days to go into detail on, but I want to cover it because it's very important. First off, what is a linear load? A linear load is where the load or the current wave shape linearly follows the utility sine wave voltage. Current can differ in magnitude and power factor phase angle. But as you can see on that example waveform, the current is basically following the voltage. It's pretty clean. Some typical linear commercial loads are induction motors across the line, of course, incandescent lights, resistant heaters, electromagnetic devices, and transformers. What is a nonlinear load? Harmonics are basically defined as a deviation from the ideal fundamental AC line voltage and current waveforms. And again, if you look at that example waveform, that's the current representation of a 6-pulse drive or a nonlinear load. And nonlinear loads contain current harmonics, which can cause voltage harmonic problems for other users. And the key thing is there, other users. Nonlinear loads, a couple examples are welders, arc furnaces, UPS and DC power supplies, DC drives, and AC drives. And with the more frequent use of AC drives and increased number of AC drives, harmonics has become more of an issue. I'm not going to go into great detail on why there's odd harmonics and all the calculations. That's the ground level stuff. But basically, what you want to know is that AC drives and anything that doesn't use the entire waveform coming in causes harmonics. With a 6-pulse AC drive, the reason that those harmonics are is because if you look on that 6-pulse rectifier, the front end or converter, we're using SCRs, and those SCRs do not conduct current through the entire sine wave. They have turn on, turn off, and what happens is you see the result of that in the distortion of the waveform. There's the link choke shown in the block diagram. One other thing I want to note, that if you put a link choke on, or the drive comes with a link choke, the benefit of adding a line reactor above and beyond just a link choke is that line reactor sits out in front of those input SCRs. So you're protecting the SCRs with a line reactor, whereas the link choke is after the SCRs. And again, you can see in the note there, the input current to a 6-pulse rectifier is non-sinusoidal and produces current harmonics, which flow back into the power system. Before, I noted that one of the problems with harmonics is it affects your neighbor or other users. It's not as big a deal as an industrial environment, but when you're looking at a pump station, or an example where you're in a semi-residential area, affecting your neighbors can be a no-no. Here's an example of some input current of a 6-pulse drive. And you can see the voltage waveform on the bottom is relatively clean, but the current, because of those SCRs on the converter in the drive, is not following it. And the first example is a no DC link choke. And you can see the current total harmonic distortion is about 80% at full load. Without a DC link choke, your total harmonic distortion depends on source impedance, and the rectifier diode turnoff causes voltage wave spikes on the voltage waveform. For drives with less than 5 horsepower, there's not much of an impact on utility. And I'm going to say here that harmonics is a system problem, and you need to look at it holistically as the system, the entire power distribution system. The next waveform is a standard configuration with a DC link choke, and you can see that the current total harmonic distortion is reduced to 32% at full load. With a DC link choke, the THD is independent of the source, better power factor, and it minimizes the input voltage distortion. Again, a DC link choke is still not protecting those SCRs in the front end of the drive. Now, why are we talking about this, and what problems do harmonics actually cause? The frequency and the harmonics, they increased utility current requirement, so you may have to oversize your transformers and oversize things, which gives you an inability to expand. Component overheating, the transformers and wires, again, they're not designed for the high frequency up into the higher harmonics. Nuisance tripping can cause lost productivity. You can have multiple equipment malfunctions. You transfer the noise to other loads. And again, there's that possibly even other utility customers. There's IEEE 519, which I'll get into a bit, but they, that's what IEEE 519 is about, not affecting your customers, and that's some utility companies are very strict on that. If you add VFDs or incorrect meter readings and relay malfunctions, communication or telephone interference problem, again, it's harmonics or noise, and that could cause interference. Excitation of power system resonance, creating overvoltages, and voltage flat topping problem. The nuisance tripping, causing lost productivity. I have a real world example of that. When I was at a injection blow molder, I worked at a plant, and we had a bunch of these little takeoff conveyors. They were like 1-2 horsepower, and we also had a couple 100 horsepower cross the line starters, and the combined noise that was there would keep tripping out those little 2 horsepower, 1 horsepower takeoff conveyors. And if you're familiar with injection blow molding, just because the conveyor stops, I need to clear the molds, and there'll be bottles flying everywhere. So basically what we did was I went in after I realized what was going on, and I put some line reactors in front of those little drives, and didn't have to worry about the noise and everything else. Some of it was transient, some of it was harmonics, but adding line reactors in front of those little drives stopped the overvoltage faults and the problems associated with it. Now I'm going to talk about practical guides for harmonic compliance. First thing you want to do is you want to perform a preliminary harmonic analysis and then explore the effects of the various harmonic mitigation methods, which I will go into detail on. You need to identify your required point of common coupling and apply the techniques most cost effective for that point of common coupling or your location. Take the time to understand the benefits and drawbacks. There's various mitigation solutions. You want to meet the requirements of the application, whether it's IEEE 519 or you just want to reduce your harmonics, and then realize the negative effects that are by the chosen harmonic solution. And consider an active front end if the application requires regenerative operation and harmonic compliance. More practical guides: add a line reactor or DC link choke if possible to any unbuffered 6-pulse drive or group of drives. And again, unbuffered is anything without a DC link choke. Consider the use of an active filter on a multiple drive system or MCC lineup to correct for harmonic distortion. For passive filters on generator power, or for passive filters overall, you want to put a dropout contactor on the filter capacitors. If you are running lightly loaded with the VFD with a passive filter, even on utility power, it causes a leading power factor. So anytime I put a passive filter on an application, I put that dropout contactor, and when the VFD is lightly loaded, we drop out the capacitor. How do you know if you have harmonics? Again, there's software analysis, which I'm going to cover a little bit. You can measure the actual percent total harmonic distortion with a power quality meter, such as like a Fluke 435 or any other trending power meter. You can put it on where you decide your point of common coupling is, or in front of a process, and see what your total harmonic distortion is actually measured at. This is a spreadsheet. It's the advanced harmonic calculator available from Rockwell, and we'll be sending it out to you. Excuse me. What it is, you go in, and as you can see, I have highlighted there, you put at this one, I considered the point of common coupling. I wanted to look at PCC2, and those are default values when you open this up from a blank spreadsheet. But you can put in your user transformer, your generator power, and you can see right now I have no loads on this calculation, so IEEE 519 compliance is yes. My total harmonic distortion, both voltage and current, is at 0. So what I did, and again, this is just an example, I threw 350 horsepower, total horsepower of 6 pulse buffered without a line reactor into the system. That can be 350 horsepower single drive or multiple smaller horsepower. My total 350 horsepower. There's actually, if you look on the far right, there's a link where you go, and if you look on the bottom, there's a tab, the VFD loads, where I put in my VFDs, horsepower and quantity, and what type of VFD it is. And you can see as soon as I put that on there, my IEEE 519 compliance went to no, and you can see I have 33% current distortion. Now, because I'm an Allen Bradley drive specialist, I decided I'm going to take this 350 horsepower and assume that it's a single 350 horsepower VFD. I took that same 350 horsepower and I threw it on a TL, or a low harmonic drive, and I instantly went back to yes. Now, normally I would have other cross the line starters, and I have a tab and a sheet that I calculate. I basically take my one line diagram and I put in all my values in the different places where it fits. I want to jump back real quick. If you look on this, when I put in the 350 horsepower without a line reactor, at the very bottom right there, I have active filter on PCC2. That 103.2 is a calculated value. That tells me if I were going to go with an active filter, I would need about 103 amps of corrective current to meet IEEE 519. So with all that said, I've identified what problems harmonics cause. How do you reduce them? You put a DC link within the drive. You add a line reactor. You can use a passive filter, an active filter, a multi-pulse front end, or a low harmonic VFD. This is a drive with the DC link choke, and there you can see the DC link choke in between the AC to DC converter. And again, that doesn't protect the front end of the drive, but it's in there. It does reduce typical current distortions about 30 to 40%. And you can see the waveform again down below, how that DC link choke, the 30 to 40% of distortion that nonlinear load causes. This is putting a 3% line reactor in front of it, and it also has the DC link choke. You can see my distortion drops down to about 20 to 35%, and a line reactor, especially without, if your drive doesn't have a DC link choke, is a big help. And typically, again, if you're dealing with harmonics, this waveform is shown with 3%, but as I stated earlier, 5% helps with harmonics more. And when I use that spreadsheet and I'm doing a software analysis, if I have other loads, if I put 3%, I might not get to the distortion I want, but if I add a 5%, I might drop to where I need to be. This is a block diagram of a passive harmonic filter. Typically, you can get down to about 5 to 8%. You can see the waveform starting to look a lot better than with just a line reactor or a DC link choke. This is an active harmonic filter, and that you can get down to 3 to 5%, and the way these work, they're actually, just as the name implies, they're active. They monitor with CTs, and when the harmonics get bad enough, they inject current to offset it, and you can see the waveform looking much better. This is another example of an active filter, and the good thing about active filters, that's why I mentioned earlier, you can put it in a lineup of drives or in an MCC. You can have multiple AC drives, even a DC drive, or any nonlinear load for that matter. And that active filter, if sized correctly, you can, in fact, meet IEEE 519 or reduce your harmonics. This is the example of how to mitigate with a multi-pulse. In this case, I used 18 pulse. There used to be 12 pulse, but 18 pulse is the more common now. And you can see the complexity of it. There's an auto transformer. You have a diode, 18 diodes, a front end that has they're mounted on a heat sink. You got cooling fans. You have a line reactor in front of it. You can get down to 4 to 6%. They meet IEEE 519 typically. And then an active front end or low harmonic drive. I'm showing you our example here, typically less than 5%. And if you look at bullet 2 there and number 2, it's got an LCL filter built right into the drive enclosure itself. This is one of our larger frame sizes, but we have them down to about 10 horsepower as paddle mount. So, and again, it's a TL. It's guaranteed to meet IEEE 519. And again, I just want to touch on a couple of the bullet points, the benefits of the different harmonic mitigation hardware. With an 18 pulse or multi-pulse, we see that most often on specifications because it was the popular way to mitigate harmonics. It's larger and requires more space. And with an 18 pulse, you have typically long delivery, and it's a single point of failure. The long delivery is usually based on that auto transformer that's used. We can get the DC input drive and build the rest of the drive, and we'll be sitting there waiting for that auto transformer. Passive filters are suited for single applications, ratings less than 125 horsepower. They're very easy to get. There's numerous suppliers. You can run the VFD without it by bypassing it, and you'll be producing higher harmonics until you get it repaired. Active filters, they're showing up more on specifications. They're cost effective for multiple VFDs or installations in MCCs. That's why I showed that one slide with the active filter and multiple VFDs. Rockwell works with a couple of Encompass partners. They can actually install it in the MCC. The VFD can run without it, or multiple VFDs can run without it, and you'll be producing higher harmonics until it's repaired. And then the active front end, low harmonic VFD, they are widely accepted in Europe because of their space requirement, and they're becoming more cost effective and readily available in North America. That's been a trend over the last year and a half, 2 years. Allen Bradley makes the TL. There's other manufacturers that make low harmonic drives. Excuse me. Here's a nice little bar chart of the mitigation techniques, the hardware, and the dashed red line is the typical IEEE 519. It used to be general hospital, but now the general guideline is 5% is the limit. And you can see the different mitigation hardware, whether it's a 6 pulse without a choke, the high harmonic distortion, the 6 pulse with DC link choke still high, everything right down to the passive filter, which you may or may not meet IEEE 519. And then the last three, the red ones, you have the active front end, the 18 pulse, multi-pulse, and the active filter product. If you look at the cross trend, the three in red are very close now. The higher cost goes to single drive. If you have a single drive, you're going to do an active front end or an 18 pulse. Whereas if you have a multiple drive lineup, you may go with an active filter. But again, if I need to meet IEEE 519, I have to look at my system, I have to do the analysis, and then I look at my mitigation and what's the benefit and drawback of each device. This is another way of looking at the same harmonic mitigation hardware, and what's showing here is the typical harmonic distortion in the top row, whether it meets IEEE 519, the efficiency of that hardware. The important one on this is the overall size, which I mentioned 18 pulse drives, and some of the other stuff is not as space saving as the low harmonic drives. You can see that if you look at the example here, the 6 pulse with a DC link choke is the 1.0. Everything else is based off of that. So an active front end drive, low harmonic drive, is 1.5 to 2.5 times bigger. 18 pulse is 3 to 5 times bigger. Passive filter can be 2 to 6, and then an active power filter is 2.5 to 5. The other one I want to look at is the cost effectiveness. And again, the active power filters, lower cost for multiple drives. The lower cost for IEEE 519 on the low harmonic drive. And then one other thing, this yellow right here. Sean, can you see my mouse?
Yes, we can.
Okay. I want to point this out, the passive filter for potential system resonance. Onesie, twosie is okay on a passive filter, but if you're looking at passive filter for multiple drives, there's a chance that you can cause additional resonance in your power distribution system. So at that point, you would want to look at one of the options that is no. And again, that's all about sitting down, taking a look at what your power distribution system, what you need to accomplish as far as reducing harmonics, and coming up with the best solution. Okay, all those harmonic mitigation hardware I talked about, whether it's a low harmonic drive or a line reactor, Rumsey and Allen Bradley / Rockwell, and there's some power product partners that we work with very closely. They're Encompass partners for Rockwell. They're partners with us. I just wanted to bring up some of them. You may be familiar with them. TCI is Transcoil. They have line reactors. They have passive active filters for both the front end. They have filters for the motor side. MTE, line reactors, and passive and harmonic filters. Mesta Electronics, which was a guest speaker for the presentation on meeting harmonics with an active filter. They make the active filters. Schaffner makes some EMI filters. They also make an active filter. Acme Electric makes the isolation transformers, which is an option that I did not discuss, but it's always something that you can take a look at. And then Hammond Power Solution, they make line reactors and isolation transformers as well.
Hey, so a question that we often get, and then we can open it up to everybody else as this comes back up. Hey, I'm installing a drive or a set of drives. Do I have to have an input line reactor? How would you answer that?
How would I answer that?
Yep, that's a question that comes up an awful lot.
If I look at the 1321-TD001, it's recommended one reactor per one drive to reduce crosstalk. Have I seen one reactor, multiple drives? Yes. The official recommendation is to reduce crosstalk. You put a line reactor in front of each drive.
Okay. Fair enough. So are you sort of at the end there? We can open this up to any conversations. Okay, go ahead.
You can see it now.
Yep.
And I just wanted to bring up the two other locked-in series power webinars that we have coming up to go in more detail on the load side. The May 26th, we'll have the VFD protect your motor, and then also for MCCs, what to watch when adding buckets to your existing MCC on May 28th. Thank you.
All right, sounds good. So with that, I mean, I know we have a number of people on the call. Are there any questions specific for Rick or anybody else on there of things that have come up in the field that you'd want him to kind of answer or talk to?
Yeah, question. This is Mark Rogers from Comores.
Hey, Mark,
Hey, Mark.
Hey there.
we can hear you.
Yeah. Okay. Recent project that I did for our Fayetteville, North Carolina plant, where we had some fairly large drives at 40 volts, 200 horsepower, say. And one thing that we found with some of the input devices, reactors, filters and so forth, is quite a bit of voltage drop. And this was a situation where we had on some of these drives, say, close to 500 feet of cable distance. And so, if you're dropping a substantial, amount of voltage on a line reactor, you need to make sure that your motor's not starved for voltage. And so the way that we achieved it on this project was we oversized. We were using a passive filtering device, and we oversized it to reduce the amount of voltage drop on the line side of the drive.
So you said you used a passive filter?
Yeah, it was from MTE, I believe.
Okay. Yeah, they have a very high percent. I think they're in the lines of 5 to 8% impedance. So you're going to have more voltage drop off of that than just a normal line reactor.
Right.
Did you do an analysis before you installed them?
Yeah, we used that sheet that you had up there earlier. The one that tells you whether or not you comply with IEEE 519.
Uh-huh.
And so, once we use that device, I mean, we use the passive filter at the normal rating, and so that solved the problem with the harmonics. But then we had to deal with the voltage drop, and we achieved that simply by oversizing that passive filter.
Okay.
Right.
Yeah, and that's I think one thing that you'll typically find with all of the different solutions. They all have a benefit and a detriment to a certain extent. Because one of the challenges you do run into with oversizing like input line reactors that I've ran into is by doing so, or possibly by doing so, your impedance is really associated to a full load on like a line reactor, so your impedance will drop if you're putting less current through it than its ultimate size. So you sort of end up counteracting some of the benefits with oversizing and vice versa. But sometimes you have to do it, right? So it's very much dependent on the application. In some of those cases, maybe the actives might have been a good option too. But there's no right answer in a lot of cases, which is one of the things that I guess is just part of applications.
Okay, thanks a lot for your
Well
answer.
said.
Yeah, if I had mine, one of the reasons I asked about the input line reactor question, Rick, is if I owned a plant and was responsible for making it run every day, like many people are that are on the call, I would want a line reactor in front of every drive. However, that's not always realistic, both due to a cost perspective, just a pure space perspective. And you just run into a lot of those cases. Just like if you go back to long ago, it was, fuses were the only appropriate input device, and they've since changed to circuit breakers. But that was because back in the day, things were more repairable in drives. Small drives, 1-2 horsepower drives, you don't repair anymore in most cases. So things have changed over the years on some of that. All right. I guess. All right. There is actually a question here for you, Rick. You wouldn't be able to see it. It says, are Allen Bradley drives UL listed for use on 3-phase high leg open delta utility configurations?
Oh, I haven't had that question for a couple of years, and I always have to look it up.
So Jim, we will take that and get back to you specifically on it. We have your information. Yeah, that's a fairly specific question, so probably not one that's right at our fingertips.
Yeah. No, I have answered it over the years. I just can't remember it right now.
Okay. So yeah, so that one we will follow up and get back to you on. All right. Well, with that, I would like to thank everybody for tuning in today. We will have more of these locked in series every Tuesday and Thursday on different and varying topics. Right now, scheduled through the end of May. So I want to thank everybody for taking the time, and shortly hereafter, we'll make sure to get kind of an overall survey and information out, and you'll have a copy of the links and also a copy of the presentation. So all of that will be coming out here shortly. And if you have any questions, Rick Archer's contact information is there on the screen. Feel free to reach out to him at any time. All right.
Thank you.
Thank you very much, everyone.
Thank you very much.
Thank you, guys.